So so we can evaluate the optical power of a lens. This is not the same thing as the power as in work per time or energy per time. The power for a lens is just 1 over the focal length in SI units. So this is the standard power. So you'll see, and so you can say the units are for optical power is meters inverse, and this is called diopters. And so, for example, if you look on like reading glasses, like my reading glasses, I'm sure you can't see that, but somewhere on here, all right, it should say, yeah, so it says the power is equal to plus 2.0 diopters, or plus 2.0, right? And so that means the power is 2 inverse meters, or the focal length is equal to 1 over 2 meter inverse, or 0.5 meters. And so you can see this is a converging lens because it's got a positive focal length, right? Most reading glasses are converging because people get farsighted and they need the rays to be bent more to get the image into focus, and so they use converging lenses. And so a power of 1.0 means the focal length is 1 meter. That's a pretty long focal length. Generally, if anything longer than that, and you don't need any correction to your eye. And so, because you're trying to bring something into focus that's a meter away, your eyes are already pretty good. So, so this is diopters. So usually, like you'll see, common powers are plus 1.5, plus 2.0, plus 2.5, plus 3.0, and so on. 3.5 or 4. Probably it doesn't get too much higher than that. Usually this happens around age 40 to 45 or something like that. I'm about 60 and I'm somewhere in here. I have some of these and I have some of these. And so gradually, and it turns out almost unless you have some very unusual eyes, like for example, if you're very nearsighted when you're young, your eyes will sort of self-correct a little bit as you get older. But if you have sort of normal eyes, you will end up needing these just because of the way the eye works as it ages. And so that's how you count the power. And so if I do one more, if I say, you know, if I have a so if my focal length is minus 0.3, right, this is meters, right? This is a diverging lens with a focal length of minus 0.3, and the power is just 1 over f, which is 1 over minus 0.3 meters, which is minus 3.33 diopters. And so they could just do it in terms of the focal length, but they choose the power instead, and they're very simply related. So we're going to talk about the Lensmaker's equation, and this is an equation that a Lensmaker uses to make lenses. And so I'm just going to start out with some simple lenses here. And so there's a converging lens, right? Here's another converging lens, but one more likely you'd see in a pair of eyeglasses, right? And then here's a diverging lens, right? And let me make another diverging lens that you might see in a pair of eyeglasses. So let's do it like this. right? And so both of these are diverging, and both of these are converging. And you can tell because these guys are thicker in the middle than they are at the edges, and these guys are thicker in the middle than they are at the edges. A couple other things about these. These guys are thinner in the middle than they are at the edges, so these are diverging. So rays coming into these guys, right, will be sprayed outward. The ones that go through the middle are unaffected, right? Whereas rays that are coming to these guys will be bent inward, so they'll cause rays to converge. And rays in these guys, both of these guys will cause rays to diverge. A couple other naming conventions. Anything that's sides that are bulged outward like this are called convex, and sides that are going inward like this one and that one, oops, are concave. So this is a concave side, this is a convex side, this is concave, 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 convex. Hopefully you get the idea on those. And so we're going to pick a lens, and then we're going to show how the Lensmaker's equation works. So let me just draw a lens here. I'll erase this stuff. I'll start out with a double convex lens, like I had on the left right there. And right. So I don't know, something like that. So this is a piece of glass in air, and so I'll say, the index of refraction for air is equal to 1, and we're just going to do it for the glass in air for the time being. And so the index of refraction for air is going to be 1 throughout this problem, and the index of refraction for glass is what it is. We can call it anything. It's usually about 1.5 in most of the examples we do, right? And so the Lensmaker's equation is a relationship between the focal length and the dimensions of the lens. And so the relevant dimensions of the lens are the radius of curvature of each side. And so this is the front side of the lens. Usually our object starts here on the left, right? And so this is the first side. And so what we'll do is we'll draw a little radius of curvature for this guy. So there's the center of curvature. And this is the radius of curvature. So I'll call that C1 and R1 for the center of curvature for surface 1. Right? Similarly, I'll just draw a slightly different one. Here's R2 and C2. This is the center of curvature for the second surface. And so it turns out the focal length for this lens is given by 1 over f is equal to n minus 1, where n is the index of refraction, times 1 over r1 minus 1 over r2. That's how it's calculated. And so if you remember what we did with the mirror, this is for a lens, right? This is the Lensmaker's equation. Let me just write that down. I still have to show you how to use that. But if you remember, we said for mirrors, this is an aside. All right, for mirrors, we said the focal length is r over 2. And so if we wanted to, we could say 1 over f is equal to 2 over r. It's more complicated for lenses. First of all, you might imagine that for a lens, the index of refraction is involved, whereas not for a mirror. You don't need an end in a mirror because the mirror just reflects something off the surface. You need the geometry, the radius of curvature, to calculate the focal length, but that's all you need. For a lens, you need the index of refraction, and you need both radii of curvature because both affect how the rays are bent as they travel through travel through the optical path. And so there are a couple of rules for this that I'm just going to have to write down. So the radius of curvature just depends on how big a circle that is. And so that's just a property of the curvature of that circle, right? Sorry about that. So R1, in other words, the radius of curvature of for this surface can be either positive or negative. It's positive if the center of curvature is on the same side of the surface, this surface, the surface 1, as the outgoing ray. So a ray that comes in here, right, is refracted this way somehow, and so the outgoing ray is on the same side of the surface as the center of curvature, and so for this guy, R1 is greater than 0. If this had been a concave surface, the center would be over here, and it would be on the opposite side of the surface from the outgoing ray, the ray is always going to go through the glass, and so when the ray goes through the glass, it's on this side. If the center of curvature is over here, we use a negative radius, and so I should say down here, otherwise, R1 is less than 0. And it's the same thing for R2. So I'm going to erase that equation, but I'll put it back. I say, look, R2 is greater than 0 if C2 otherwise, the radius of curvature is less than 0. So in this case, notice if I follow this ray on through, I don't know what it's going to do. It's going to bend here, something like that. It's going to keep going through, and then it's going to bend down some more, maybe, and it's going to come in here somehow, right? And so when I get to this surface, the outgoing ray is on the opposite side of the center of curvature for this surface. So again, notice this is the radius of curvature for surface 2, and this is the radius of curvature for surface 1, right? And so for surface 2, the outgoing ray is on the opposite side of this surface from its center of curvature, and so we use R2 is less than 0. So in a double convex lens, R1 is greater than 0, and R2 is less than 0. So I'm going to do an example with that now. So we're going to use the Lensmaker's equation for a lens made of glass. And if you remember the Lensmaker's equation, it's 1 over f equals n minus 1 times 1 over r1 minus 1 over r2. And we have to be a little bit careful about our r1 and r2 for the following reasons. So I'm going to draw an optic axis here, and then I'm going to put a lens on it. So here's my optic axis, right? And now I'm going to draw a lens. I'm going to draw this one sort of weakly curved, and this one strongly curved, like that. And then this is my surface 1, so I'm going to pick a center of curvature out here somewhere. And so that's my center of curvature for R1. So that's C1. And I'm going to have a shorter center of curvature here because it's more R2 is more curved. And this is R2, and this is C2. And so we're going to say the magnitude of R1 is 20 centimeters, and the magnitude of R2 is 10 centimeters. It's got a shorter radius of curvature and a longer radius of curvature. but we still have to work out the sign, whether these are plus or minus, because we have a rule for that. Our rule is R1 is greater than 0 if the center of curvature is on the same side of the surface as the outgoing ray. And again, this is my surface here. And so here's an incoming ray to surface 1, and there's an outgoing ray. And so the outgoing ray is on the same side of this surface as the center of curvature. And so I can just write R1 is equal to plus 20 centimeters, or just 20 centimeters. Now to fill out this formula, I've got the index of refraction. I'm assuming it's glass and just using a typical number for glass, right? Now I've got to figure out what R2 is. Well, when the ray hits R2, any ray, I'll just draw this one continuing, but I can pick any one that's gonna refract again. Excuse me, at that surface. And so the outgoing ray at this surface, for surface 2, is on the opposite side of the center of curvature for surface 2. And so I would say R2 is equal to, is R2, so R1 is greater than 0, R2 is less than 0, and so R2 is minus 10 centimeters. And so now I can evaluate this. Now I have N and I have R1 and R2. I can say, look, 1 over the focal length is 1.5, that's my index of refraction, minus 1, times 1 over 20 centimeters, minus 1 over minus 10 centimeters. So I've got a minus sign here. I should just erase that, right? So you don't think that's an equal sign or something. And I've got a minus sign here. And so this gives me 1 over the focal length is equal to 0.5. That's what's in parentheses here, times 1 over 20 plus 2 over 20, or 3 over 20 centimeters, right? And so what's the easiest way to do that? So a half is 3 over 40. Is that right? And so 1 over F is equal to 3 over 40 centimeters, or F is equal to 40 centimeters over 3, which is 13.3 centimeters. So that's the focal length I get for this lens that has 2 different radii of curvature. Notice that if I flip the lens over, right, and so let's just redo the math here a little bit with the lens reversed. So that was our focal length. Let's reverse the lens. And so if I flip the lens over, I'm just going to do a little eraser work here, and it's going to be ugly, but let's go ahead and do it. All right, I'll just erase the whole thing. Too complicated. Put this guy back in. So now I've got the long radius of curvature on this side and the short radius of curvature on this side, right? And so my R1 is 10 centimeters, and my R2 is 20 centimeters, right? And once again, just like before, R1, the center curvature is on the same side of the outgoing ray, and so this is 10 plus 10 centimeters, right? And R2, this guy, when a ray comes through here, I'll just draw the rays, right? Here's a ray coming in that gets bent here, right? Here's a ray leaving this surface and going off this way, right? And so this ray is on the opposite side of the center of curvature from this guy, and so R2 is less than 0, and so R2 is equal to minus 20 centimeters. And so if I evaluate the focal length, I get 1 over F is equal to, again, it's the same index of refraction, so it's 1.5 minus 1 times 1 over 10 centimeters minus 1 over negative 20 centimeters, which is equal to 0.5 times 3 over 20 centimeters, because that's 2 over 20 plus 1 over 20. And so that's 3 over 40 centimeters. And so F is equal to 40 centimeters over 3, which is 13.3 centimeters. So it's exactly what we got before. It doesn't matter which way I orient the lens, I get the same focal length whichever way I hold it. That should be your experience flipping lenses over. Okay, so let's pick a different surface now. So we're going to do an example, a slightly different example. We're going to have a lens that's convex and concave. And so I'm going to draw the second surface here and the first surface here, and then we're going to reverse it in the next one. And so here is R1 and C1, right? That's the radius. This is the first surface that the light gets to, because the object starts on this side, right, on the left side. It should come out with a negative focal length because it's a diverging lens. The second radius of curvature, this is less curved than this guy is, so he's going to have a bigger radius of curvature. Maybe I'll draw him down here. Looks like that. This is C2 and this is R2. Again, that's the second surface that the light gets to. And so we can say, look, just like before, we're going to say that R1, we're just going to pick a value. So let's say this is a smaller radius of curvature. Let's use 6 centimeters. And we'll say is 12 centimeters, or yeah, 12 centimeters, that's fine. We haven't figured out, I put those there because we're saying the magnitude is 6 and the magnitude is 12. We've got to figure out what the sign is, the SIGN. And so we just use our rules. For the first surface, here's a ray coming in. The ray crosses the surface, right? And so it goes out like this. And so for R1, the center of curvature is on the opposite side of the outgoing ray for that surface. And so I can say R1 is less than 0. And so R1 is equal to minus 6 centimeters. Technically, it's the same thing for R2, right? When it comes across here, it gets refracted some more, and it's on this side, but the center is on that side, and so I can say R2 is minus 12 centimeters. Right. And now all I have to do is evaluate, right? I can take this this formula, 1 over F, is equal to n minus 1, so that's 1.5 minus 1 times 1 over, so this guy, minus 6 centimeters, right, minus 1 over minus 12 centimeters. And so that gives me 1.5 minus 1 is 0.5, or a half. So this is minus 6 minus 1 over minus 12, which is the same thing as minus 6, a sixth, negative a sixth plus a 12th. So it's minus 2/12 plus 1/12 is minus 1/12. And so if I divide that by 2, I get minus 1 over 24 centimeters, which is 1 over F, and so F is equal to minus 24 centimeters. And so on my next slide, I'm just going to flip it over and show you that it comes out the same. And so when you evaluate the focal length of lenses, you have to make sure you get the signs right and get the signs right in these equations. And it shouldn't matter which way the lens is. The lens behaves the same way either way. It's just if you want to calculate it, you got to make sure you get all the signs right. So now we're going to redraw that lens flipped over, right, like this, right, where the radius of curvature of this guy, this is now C2 and R2, is here, right, and this guy here is C1 and R1. And we already said that the magnitude of R1 in this case is 12 centimeters, because that's the first surface that I'm hitting, and the magnitude of R2 is 6 centimeters, which was flipped before, because when it's flipped this way, the curvier part is the first one you get to, right? And so in this case, when the ray comes in this way, the center of curvature for R1 is on the same side as the center of curvature, and the center of curvature for R2 is also on the same side as the center of curvature, and so they're both greater than 0. And so it's the opposite of what I had a minute ago. I have R1 is equal to 12 centimeters, and R2 is equal to 6 centimeters. And that gives you a focal length that you just calculate the same way. It's 1.5 minus 1 times, so it's 1 over R1, which is 1 over 12 centimeters, minus 1 over 6 centimeters, which is 0.5 times 1 over 12 centimeters with a minus sign, or 1 over f is equal to minus 1 over 24 centimeters, which gives f is equal to minus 24 centimeters.